ATAL or directions?
Audiology at All India Institute of Speech and Hearing, AIISH, Mysuru. He completed his bachelor's, master's and PhD degrees at AIISH and later pursued research fellowship at Northwestern University, Illinois, USA. With over 15 years of research experience, his work focuses on how the brain processes sound, speech perception in difficult listening conditions, auditory learning and hearing disorders. He has published more than 60 research papers in national and international journals and has completed several funded projects from BSc and AIISH. Dr. Ajith has guided many PhD scholars and continues to contribute to the areas such as auditory physiology, psychoacoustics and diagnostic audiology. We are truly honored to have you with us today, sir. On behalf of the organizing committee, I wholeheartedly welcome you. I request you to take over the session. Over to you, sir. Thank you.
This always happens to us. I thought in engineering college this wouldn't happen. The slides will never come up. Am I audible? So I need the mic. Am I audible? Yes. Yeah. So, good morning everyone. I'm Professor in Audiology at All India Institute of Speech and Hearing. So, I don't know how many of you heard this profession of audiology. As the name suggests, audio and logy. It's two words. Audio is related to the sound. Logy is studying the sound. Basically studying the how sound is processed in the ear and in the brain, and what are the disorders associated with that, what happens when a particular disorder associated with this. So in this series of FDP, I think this is the first one where I try to discuss something on engineering marvel of the ear. Ear is considered as one of the mechano-electrical marvel where most of the signal processing that we are studying now, like the fast Fourier transformation or the impedance matching, all of that takes place naturally. And whenever there is a certain disorder of the ear, one of these mechanisms break down, and via some assistive devices we are trying to compensate those mechanisms. All of that I think you would learn in the coming series. Today what we will discuss is how a normal ear processes sound, what happens when the sound enters into the ear, and very gross anatomy of the ear and physiology of the ear, for you to understand further what happens when there is a breakdown and what are the mechanisms or what are the systems that are available to cope up with the breakdown. So to start with, the three functions, like we all know that some basic characteristics by which a sound can be defined is three: its frequency, its amplitude, and its duration or the phase of it. For ear to process sound, ear needs to process all these three aspects: the frequency, dynamic, the intensity, and the time or the temporal resolution. Now by frequency I mean like when I am talking to you, my vocal cords are producing certain range of frequencies. When you are hearing a noise outside, it is certain other range of frequencies. Or when you are hearing a fan noise, it is certain other frequencies. Ear must have a capacity to differentiate these frequencies, see what is important and what is not. For example, all of you are hearing my voice clearly. At the same time, you are also hearing the fan noise. Probably somebody speaking over there also you are hearing. But you are not paying so much attention to that noise or the fan noise, I hope so, to my voice, because you have that innate capacity. The ear processes those sounds, filters out whatever is irrelevant, filters in whatever is relevant, and sends only that information to the brain for the further processing. So for that to happen, ear needs to distinguish each of these frequencies very finely. Like it has to do a fast Fourier analysis, take out only certain bands of frequencies which it thinks is important, and remove those bands of frequencies which it thinks it is not important. And this important and non-important is a relative term. when you are hearing my speech now, certain band of frequencies between 500 to 2000 or 2500 hertz is important to you. But at the same time, when you listen to a music, it becomes 1000, like 500 to 2000 becomes unimportant. The very high frequencies becomes important. So what is important at a particular time need not be important at another time. So ear has this capacity to weigh different frequencies, differentiate different frequencies, give different weightages to the different frequencies and process that. And also to do this over a wide dynamic range. For example, the minimum sound that we can hear, that we call as a threshold, that is the minimum amplitude of the intensity that we can hear, and the maximum sound that we can tolerate, which is the uncomfortable level. This is by about 10 to the 14 times. That is the minimum sound we can hear is about 20 micropascals. The maximum sound that we can hear, the sound is a pressure wave. So we can measure sound in terms of decibels or in terms of pressure or the intensity. So in terms of pressure, the minimum sound that we can hear is about 20 micropascals. The disturbance of 20 micropascals in the atmosphere is perceived as sound by the ear. The maximum sound that we can tolerate without causing pain, like for example, if you hear a very loud noise, it does causes pain. So that level is called uncomfortable level. That is about 20 pascals. So this difference is about 10 to the power 14 times. And ear can accommodate all of these pressures or the intensities very well within that dynamic range, and making us to hear from very soft to the very loud intensities. Even the very modern day microphones fails to do it. That's why you may hear peak clipping in most of the microphones or the amplifier systems, because if you make it very sensitive, for example this microphone today, if I speak it very soft, it will not pick up. If I speak very loud, there will be peak clipping and you will start hearing the distortion. So that never happens to us. You don't hear peak clip sounds in your ear. You always hear it is well within the dynamic range. For that, ear does a very good compression amplifier. Ear works like a compressive amplifier. We'll come to that later. And also ear has a very high temporal resolution. That is, like for example, if I say, what is your name? My entire sentence gets over within about 1 second maximum, or within about 800 to 900 milliseconds. So in this 900 milliseconds, I would have uttered what is your name, 3 words. Even in one word, like what, like wo is a sound, ter is a sound. The entire word would have come in within about 100 to 150 milliseconds. So the ear needs to process how the frequency and the intensities are changing in such short spans of time. So that ability is also present in the ear. So we will see what are the different anatomical and physiological mechanisms that makes this possible. And in disordered population, almost always it is one of these 3 that gets affected. It could be a frequency resolution, it could be the perception of intensity, or it could be perception of the time, or they wouldn't be able to process the sound as fast as what me and you can process. One of these can get affected, or there are some disorder where all of this also can get affected together, depending on what parts of the ears are getting affected. So how many of you know like a very gross anatomy of the ear? None. So this is the I think this picture should be familiar whenever you study something about sound or the ear. First picture, whenever you Google ear picture comes, typically ear can be divided into the 3 portions: the outer ear, the middle ear, and the inner ear. So what you are seeing outside is the outer portion of the ear. That has a small canal, which we call as an ear canal or the auditory canal, which goes inside. That has a small drum at the end of it, which is called the eardrum. Now till here, the sound is in the form of the echo. When the sound enters the ear, till this point, sound is in the form of the acoustic energy. That is, the sound is in the form of sound waves. Once the sound waves hits the tympanic membrane, the acoustic energy gets converted into the mechanical energy. This mechanical energy gets transferred into the 3 bones called malleus, incus, and the stapes. These 3 bones are arranged in a particular way. We will come to that later. And the last bone, which is the stapes, which is one of the smallest bone in the human body, gets connected into another structure called cochlea. Cochlea is named in this way because a cochlea which is a snail shape, which is like a snake bound around itself. It has about 2.5 turns. So till the cochlea, the sound is still in the form of mechanical energy. The sound gets converted from acoustical to the mechanical energy at the tympanic membrane, remains as a mechanical energy within the middle ear. This portion is the middle ear. Goes as a mechanical energy into the cochlea. Still it is in the form of mechanical energy because this cochlea is filled with the fluid. Cochlea is filled with the fluid, and this motion causes the movement of the fluid. So it's still a mechanical energy. At the cochlea, the sound gets converted into the mechanical energy gets converted into the electrical energy. That is, it gets converted into the action potentials in the auditory nerve that can reach the brain and make sense of what is being heard. So till about this point, the sound is in the form of mechanical energy, and from here onwards, the sound gets converted into the electrical energy. So all of this system has to work in unison, and all of this system has to work distortion free for us to hear speech or any sound for that particular matter without any distortion. So let's see what are the different parts of the ear are doing. So first part will go inner first outer ear, middle ear, then go to the inner ear and see what happens. So first part the outer ear, as I said, what you see outside, that is this portion which is called as the pinna, and the small canal which goes inside is called as the ear canal. Now this acts like a funnel, and this acts like a tube which is closed at one end. So the tube closed at one end has got certain resonance properties. You must have studied all of that. It has got a half wavelength resonance properties. So this behaves like a half wavelength resonance, and it amplifies or it increases the amplitude of certain frequencies of sound. Apart from that, because we have 2 ears, all of us have 2 ears. Starting from very lower animals, we have 2 ears. Now, like, have you ever thought what is the use of 2 ears? Even if you close one ear, all of you close one ear, can you hear me? Whatever I am speaking, you should be hearing it very clearly. So, what is the use of 2 ears? Balancing. Okay, balancing has 2 meanings. One, to balance while walking or while standing. That balance are you speaking, or balancing of the sound? Ear also has a balancing function that we are not touching today. You are able to stand, sit, walk is because of another functioning of the ear by a portion of the ear which is over here, which is this portion of the ear. We are not talking today. This is the portion that is responsible for the balancing. You are able to stand like this. I am able to see you without move. When I move my head, my eyes are also moving along with my head because of this portion of the ear, which is called vestibular system. That balance we are not talking today. So why do we have 2 ears? Okay. The 1 ear is sufficient for us to hear, understand, learn speech, understand speech for almost all the functions. We need 2 ears only for us to make out from which part the pitch, from where the source of the sound is, or from which direction the sound is coming. Now all of you are able to make out that I am talking to you from front. Even if you close your eyes, you are able to make out that I am talking to you from the front. When I move towards the right, you are able to make out that I am moving from the right side. Or when a vehicle honks from the left side, even when you are not facing the vehicle, you can make out that the horn was on the left side, or horn is on the right side, or the fan was on the top, not at the bottom, or somebody calls from the down floor. You are, even without seeing that, you can make out that the sound is coming from the down. So that is called localization of the sound. That is, we are able to locate the source of the sound, and for this purpose we need 2 ears. And this happens primarily because the 2 ears are situated in the 2 different locations of the head. If both the ears are on the same side of the head, this is not possible. Because we have 2 ears on the 2 different sides, the 2 external ears are present on the 2, both the internal ears are present almost at the center. If I make a drill over here, both our internal ears are present somewhere in between at this point. If I just make a drill, I will go and reach the inner portion of the ear. They are present at the center. But the external ears are present at a distance at 2 lateral portions of the head. One is at the one end of the head, other one is at the other end of the head. And if you see all the animals from any invertebrates to humans, in every animal the 2 ears are present at the two extreme portions of the head. Now this creates something called interaural time and interaural level differences, which is called ILD or the ITD, the interaural level difference or interaural time difference. Simply, if there is a sound, if somebody is speaking from this side, now which ear would receive that sound first? Right ear or the left ear? My right ear will receive the sound first. Sound has to travel the distance which is equivalent to that of the head. Then it goes to the left ear. This causes a delay of about 600 microseconds for the sound to travel from this part of the head to this part of the head, because the sound cannot go like this. It either has to go around the head or around the chin and goes to the other ear. So this distance in normal humans, in an average human, takes about 600 microseconds. The ear has a capacity to distinguish this 600 microsecond to make a decision whether the sound came from the right first or sound came from the left first. So if the sound comes to the right ear first, then the brain will tell you that the sound is on the right side, you turn towards right. Or if the sound comes from the left side, brain will tell you that the sound is on the left side, so you turn towards left. And it also causes one more thing, which is called interaural level difference. So when somebody speaks from the right ear, from the right side, where do I hear loud? Right ear or a left ear? Right ear, because it will come here, it will hit this ear, I will hear this. By the time sound goes like this, certain amount of energy is lost. Right? That is called inverse square law. The distance traveled by the sound is the inverse square law. The inverse of the distance is proportional to the amount of energy that is being lost. So by the time the sound goes to the other ear, it becomes slightly softer by about 1 dB. It's very minimal. But still the ear has capacity to distinguish that and compare which ear has received higher intensity or higher loudness, whether the right side or the left side. So if the right side receives more, I will localize or make sure that the sound is on the right side. If the left side receives more, I will localize the sound towards the left side. So this function is possible because of the external ear, which is situated on two sides of the head. Otherwise, external ear has no real function. Even if I cut this entire thing, you can hear very well. You might have seen people without this portion. I don't know whether have you or not. But even without this, if you like just cup it like this, you can hear it. If you just hold it like this, you can hear it very well. So this portion doesn't really contribute to the hearing, but is important for the localization because it is situated in the two different portions of the head. And what is the cue that the brain uses to localize the sound? Two cues: interaural level difference and interaural time difference. Now you can imagine, in case of a hearing impaired, what could happen if we fit a hearing aid to only one side, or if you put an assistive devices to the only one side. The person will be able to hear speech, but will never be able to localize from where the sound is coming. Even if we put devices to both the sides, now both the sides should have a temporal resolution which is less than 600 microseconds. If it doesn't process the sound at that speed, the ears will not receive that interaural time difference or the interaural level difference. So this is one of the biggest challenge for the signal processing in the hearing aid. Probably the next speakers would do about that, where the processing should happen in real time, but in real time it should happen at the speed which is equivalent to our interaural time differences. I said 600 microsecond in an average head. There are people with the smaller heads. So in them it would be still smaller. The time difference would be smaller, because smaller the head, sound would travel lesser distance and it will go fast. Okay. So this basically a graph showing how interaural time difference and level differences are happening. So you can see that if the sound is from the right side, the red is right side, blue is left side. So amplitude of the sound is more on the left side and amplitude of the sound is less on the right side. But now what you can see is when the sound is at the center, there is no interaural time difference also, interaural level difference also. That means if somebody is speaking to me from front or from back or from the top directly or from the bottom directly, there won't be any interaural time difference or the level difference, because if somebody is speaking from the front directly, both ears will receive the sound at the same time. But still we are able to make out somebody spoke from front versus somebody spoke from back. In both front and back, there is no interaural time and level difference because sound will reach both ears simultaneously. So in that instance, what we use is called something called spectral cues. Now that happens because of specific shape of the ear. Now you can see that almost all humans have an ear in a specific shape. So there is a pinna like this, This portion is, the outer ring portion is called helix, antihelix. There is a compass. Means you don't have to know all these names, but there is a very similar shape in everybody. It is not very different. Okay. Dogs, if you take, all dogs have a very similar shape of the ear. Cats, if you take, all cats have a very similar shape of the ear. And shape of the ear of the right ear is exactly same as that of the left ear. It's just a mirror image of the left ear. Now, when the sound, for example, in the top, when the sound comes, that sound will fall on the different contours of the ear, and there will be internal reflections of the ear. So, in the ear. So, because of these internal reflections, some frequencies will get amplified, some frequencies will get nullified. For example, when the sound is coming from the front directly, so about 11 or 12 kilohertz, you will see a dip in the spectrum, and again about 17 kilohertz, you will see one more dip in the spectrum. If the same sound is when moved directly above, that is at 90 degree up, now this dip which was there at this frequency will shift to the much higher frequency. So brain uses these cues to make out whether the sound is from front or sound is from back or sound is from up or the down. So that means the brain should be able to differentiate these two frequencies from these two frequencies to make out whether the sound is coming from top or bottom. This is again another challenge for the hearing aids where most of the hearing aids today do a pretty good amplification in the low frequency region, up to 4 kilohertz, 5 kilohertz. Even there are hearing aids which work very well up to 8000 hertz, 8 kilohertz also. But the cues that are necessary for us to make front back or up down localization is at very high frequencies, beyond 7 or 8 kilohertz. So if those sounds are not processed and amplified, the hearing impaired person, if he is wearing a hearing aid, he still will not be able to localize the sound which is coming from up or down. All these things may look trivial because we don't realize how important for us to make out whether the sound is from front or back. When you are walking on the street, it becomes a life and death question at times. Even when somebody calls you from the down, for sure you know that the sound is coming from the down and you walk down. But a hearing impaired person will not know whether somebody called from down or somebody called from up. He will have to depend on someone else even if he is hearing the sound. Okay? So this is possible because of the external ear. These two functions are for the external ear. If external ear is not there, if we cut off this, you can hear very well. 90% of your all jobs wouldn't be affected. But this particular mechanism of localizing the sound will get affected. Apart from that, external ear, as I said, it acts like a tube which is closed at one end. At the one end, tympanic membrane is present. So if one end is open and other end is closed, so it acts like a half tube which is closed at one end, and it has certain resonance frequencies. So the first resonance frequency occurs about 3 kilohertz, and there is a very broad resonance frequency between 5 to 6 kilohertz, and there are multiple small resonance frequencies at the higher frequencies. These are not very important, we don't hear so much, but these two resonance frequencies are important because this is totally depends on the length of the ear canal, and in humans the length of the ear canal is made in such a way that it amplifies near the frequencies where my speech is present, or the speech has maximum concentration of the energy between 1.5 to 3 kilohertz, and ear canal enhances these frequencies. Okay. Now the hearing impaired person, for example, if you put a hearing aid, the hearing aid will go inside and it will affect these resonances. So when these resonances are affected, the speech will not sound natural. I don't know if you have some people whom you have interacted, people who have own hearing aids, their major complaint is the speech doesn't sound natural. It sounds very mechanical. One of the reasons why, because the natural resonance property of the ear gets affected, because we are going to put the hearing aid deep inside the ear canal, which will affect the natural resonance frequencies of the ear. So that is the external ear. Once the sound passes the canal, it goes and hits the tympanic membrane. Tympanic membrane is a very thin membrane which is about 1 to 2 millimeter thick. It has 3 layers. So it will fall, or the sound waves will hit the tympanic membrane, and tympanic membrane will start vibrating. Now the tympanic membrane has a uniform vibration up to about 3 to 4 kilohertz, but beyond 4 kilohertz, different regions of the tympanic membrane vibrates differently. For example, at this region of the tympanic membrane vibrates at high frequencies like this. region of the tympanic membrane vibrates at high frequencies like this, but overall the tympanic membrane doesn't do much to the sound. Whatever sound falls on the tympanic membrane, it will start vibrating just like a diaphragm of a microphone. Okay. Once that happens, the vibrations are transferred into the middle ear, which is made up of the three bones, malleus, incus and the stapes. Now, these three bones carry out a function called transformer action of the ear. Now, how we have a step up and a step down transformer? Why do we have a step up and a step down transformer? To increase or decrease the voltage or to match the impedance between the two systems. Now, here we have a air and a solid. Now, this needs to be transferred into the inner ear, which is totally filled with the fluid. Like for example, if somebody is swimming in the swimming pool and if I talk, will the person be able to hear? If someone is swimming in the swimming pool down, if I am talking, will the person be able to hear? No. Why? Because there is an impedance mismatch between the two mediums. One is air, other one is the water. Water also can conduct the sound, but the person will not hear because the sound is going from air to water and most of the sound will get reflected instead of going inside. But if some sound happens in the water, the person will still be able to hear, but he wouldn't be able to hear what I am speaking. Now, the sound which is here should get transferred into the inner ear, which is filled with the fluid. Okay? If I just push the sound like this, most of the sound will get reflected. How it will happen in the swimming pool? Because from air to the fluid, sound will not go. 99% of the sound will get reflected. So these three bones are made up in such a way that they match the impedance of the air to that of the inner ear, which is the fluid. So these three bones are arranged like this because it acts like a lever, and because of that there is an amplification of the sound to match the impedance of the external ear to that of the inner ear. Plus, the tympanic membrane is much larger, almost about 17 times larger than that of the stapes. So, if you have a cone with a larger area on top and a smaller area on the bottom, and if I press like this, what would happen? The same force applied on here will get translated to the higher pressure at the bottom. So, same thing happens in this also. So, whatever energy that is coming through the external ear on the tympanic membrane are getting transferred into the inner ear without loss of any energy because of this transformer action of the inner ear. Okay. So if there is some disorder of these bones, which usually happens, you may have seen people have with the ear discharge where there is an ear pain and after that there is a water leakage from the ear. So there is a hole in the tympanic membrane and most often these bones are eroded or lost. So in those cases, most of the sound what goes from the tympanic membrane gets reflected from the cochlea, so the person will not be able to hear. So those things can be corrected with some surgery or with some sort of a medicine. So once the sound goes from the stapes, the stapes foot plate or this portion of the stapes comes and attaches over here, which is called oval window, and it pushes the fluid which is inside the cochlea. So the fluid would move like this as soon as the stapes will move. How the tympanic membrane moves in and out, how the diaphragm of the microphone moves in and out, the ossicles or the bones also will move in and out. Stapes also will move in and out. So when the stapes moves in and out, fluid in this will also move once in this direction, comes back in this direction, and that frequency would be equal to the frequency of the sound that we are hearing. So this is called now cochlea. So now if I cut this over here and open it, you will see it like this. Three turns like this. If I cut and open it, you will see two circles here, and one circle at the top. Now this is the portion which is responsible for the hearing called organ of Corti. So this is how the cochlea looks. This is the cochlea. Okay. This portion is responsible for the balancing, which we don't talk today. This entire portion is called vestibular system. Vestibular system that is responsible for balancing, and we won't talk. So if this cochlea is cut like this and opened, you will see a cross section like this. This portion is called the organ of Corti, in which there are sensory cells that will convert the acoustic and the mechanical energy into the electrical energy. cross section of that sensory cells. So what we have done is, in this portion, this is cut like this, opened. This portion is again zoomed and shown over here. This is a small portion which is present over there. So these are the sensory cells. There are two types of sensory cells, inner hair cells, and these are called outer hair cells. So when the fluid moves like this, the fluid will apply pressure on these things. So this will move up and down. When this moves up and down, there are certain things that happens over here, and that will cause the electrical changes in the outer hair cell and the inner hair cell, which will activate the nerves, and that will carry the information into the brain. We'll see how that happens. Each of these sensory cells have got small stereocilia or the hair-like structures which are like this. So when the fluid falls on this, fluid moves on this, the stereocilia will start bending. So each of these stereocilia have connection to the next stereocilia. So when it bends, these connections will break up, and through this connection some ions will move inside the hair cell, and that will cause the release of the neurotransmitter and then the action potential. Now how all these things happen is explained by three prominent people. First, it was explained by the Helmholtz. All of you may be familiar with the person Helmholtz. He has explained so many other things in acoustics. Among them, one of the things is cochlear physiology also. So he introduced a theory called resonance theory, where he proposed that now this is the oval window, the stapes is attached over here. So you have the all structures like this aligned. Now he proposed that each of these structure acts like a piano strings. Like how a piano is arranged with a different, or the violin is arranged with the different strings. Each of these strings are acting like a piano strings. So when the vibration comes, this vibration will have a certain frequency. So a piano string which has exactly same resonance frequency will start vibrating. Rest of the piano strings will not vibrate. You may have seen some YouTube experiments where a person vibrates a tuning fork, keeps next to another tuning fork, and the other tuning fork also will start vibrating. How does that happen? Because that tuning fork has the same frequency as that of this tuning fork. Okay, that is, vibrations gets transferred. So each of these strings or the portions of the cochlea, if that has a resonance, then only that portion of the cochlea which has the same frequency as that of the incoming sound will start vibrating. All others will not vibrate. So this theory is called place theory. That is, particular specific place on the cochlea will get vibrate, will be vibrating for the sound. But this was just a theory. That time he did not have instruments or the mechanisms to observe anything. Later, a person called von Becassi, he won a Nobel Prize for this discovery, made some observations in the cadaver cochlea. That is not in the live cochlea. It's not possible even today. In the cadaver cochlea, once the person is dead, he took out the cochlea out of it, gave the sound to the cochlea, and see what does it vibrate. So he did not observe anything like a piano strings that are present in the ear. Instead, what he saw was there is a motion of waves. Okay. Now this is the cochlea, this is the fluid. When it moves like this, there is a wave that gets created within the cochlea, which will have a smaller amplitude first, gradually goes higher and higher amplitude, reaches a peak somewhere, then falls down. This is a very well-known hydromechanics. That is, if you put a stone into the water, it creates a wave. Or if you tie a rope into one section and vibrate, it will have a wavy motion. So same thing, the ear. Now this is the cochlea. Instead of putting it as a coil, we just have unwound it. We have made it open, made it straight so that you can see. So when it vibrates, these piano strings are not there. Instead, what is there is the cochlear structure will start moving like a wave. What happens, how it happens in the water, and depending on the certain properties of the cochlea, some portion will reach the peak and then it will fall down. Okay. So where it reaches the peak depends on what is the frequency that is incoming. If the incoming frequency is the higher frequency, peaks are reached in the basal portion of the cochlea, that is in the portion which is very close to the middle ear. If the frequencies are low frequency, it happens more in the apical portion, that is the portion started plotting something called tuning curves. That is what are the two different frequencies that he can differentiate on the cochlea. That is, if I give two frequencies, whether they have a same amplitude or a slightly different amplitude. So these are all the tuning curves that the Becquerel plotted. But these tuning curves are much wider than the frequencies that we can discriminate. We can discriminate very finely like this. That is, I can discriminate this frequency from this frequency or this frequency from this frequency. Whereas according to Becquerel, it was much wider. The reasons for this is, first he did the observation in the cadaver cochlea. The cochlea was not alive, or the person or the animal is not alive. In the live animal or the person is alive, there are so many other mechanisms also will happen. And because of all these discoveries were done in 1940s, it was done at a very high intensity because he did not have instrument to observe the very small variations. He had to give very high intensity so that he can measure the vibrations of the cochlea. So later, and one more issue with all these things are, as I said, already the cochlea is in the fluid. So you know that whenever there is a vibrations in the fluid, the first thing that happens is the damping. When the vibrations in the air, the damping is less. Any vibrations in the fluid will get dampened because of the viscosity of the fluid. Now, if the cochlea is filled with the fluid and if the cochlea partitions are vibrating like this, there are very high chances that it will get dampened. Or else it is very similar to if somebody plays a piano in the underwater. What would happen? No piano would sound like a piano because it will not have a fine frequency resolution. All strings will get dampened. So, in 1948, this person, he is a nuclear physicist, proposed that for cochlea to work, there should be a positive feedback. What is a positive feedback? For the dampening to reduce dampening, some amount of energy from the vibration should be taken and it should be fed back to the system so that the system will keep on vibrating or the dampening is reduced. But that was not, it was just a theory, but until 1970s and 80s it was never discovered and it was never valued. But in the 1978, for the first time, we measured something called autoacoustic emissions. That is, like till about 1970, the only function we thought of the ear is hearing. That is, we give a sound, something happens in the cochlea, we perceive the sound. But Kemp in 1978 placed a very small microphone in the ear, the microphone like this, but a very miniature one placed in the ear. When the sound was given to the ear, this microphone also picked up a sound which is coming back from the ear. This phenomena was termed as the autoacoustic emission. Auto is ear, acoustic is sound, emission is the sound that is coming out. So what is it is, when the sound is given to the ear, there is something that happens within the ear that generates a sound and that reflects back to the middle ear, then comes to the tympanic membrane. Tympanic membrane acts like a loudspeaker, produces the sound, and that sound can be now measured with the very small microphones that are being kept in the ear. Nowadays we use this for all neonatal hearing screening. This could be produced only if the person is hearing the sound. So if the baby, I can ask you whether you are hearing or not, but I can't do the same thing with the babies. They will not tell whether they are hearing or not. So we keep a small microphone in the baby's ear canal, give a sound. If the microphone can pick up the sound, we are sure that baby is hearing the sound. So this test can be done as soon as the baby is born, and we are able to say whether the baby is hearing or not, even like 1 hour after the birth. And if not hearing, the baby can be treated immediately so that no further speech delays will happen. If with the hearing delay, the accompanying delay is the speech. If the person is not hearing, they will not learn speech. So that is why the deaf and dumb comes together, but it's not deaf and they are not dumb. They are just deaf and mute. They are not speaking because they are not hearing. But if we know that he is not hearing in the first few years of life, we can easily treat and make them hear and speak very well in comparable to the normal hearing person. For that we use this particular test, autoacoustic emission. But this test is a byproduct of this positive feedback mechanism that the Gold spoke. That is, some portion of the energy from the cochlea is taken back, fed back to the cochlea. In that process, this cochlea becomes unstable. Like how if I take the microphone near the speaker and keep it, what would happen? You will hear a squeak while microphone runs into a saturation. The same thing when the nature takes some portion of the vibration, feeds back into the cochlea. There are times the cochlear vibrations becomes unstable and they continue to vibrate even after the stimulus is stopped. Like how you hear a squeal. That vibrations are transferred back into the middle ear, then to the tympanic membrane, which acts like a cone of a loudspeaker, and that produces a sound. That sound we don't hear every day because it is very low in intensity or it is below our threshold. But by keeping a small microphone, we can measure, and that can be used as a test. And also, does the internet work? You can see this later. So, how does this happen? This happens because of a specific sensory cells. I showed some sensory cells. Specific sensory cells in the cochlea called outer hair cells. Most of our sensory cells are have a response to the sensory stimulus. For example, when you see retinal sensory cells will get activated, they'll convert the light into the electrical energy, and you see what is around you. Similarly, till about 1980s, it was thought that ear also has same concept. When the sound comes, sensory cells of the ear gets activated. So that will transfer the information to the brain, and you hear the sound. But in 1983, this person observed that when the sensory cells of the ear are stimulated via current or via sound, they change their shape. They act like a piezoelectric material. That is, piezoelectric material, when given electrical shock, they change their shape. So sensory cells of the ear also either elongates or reduces in its size whenever the sound comes on it. So this change in the shape, what happens? The change in the shape will act like a positive feedback. So this movement of the hair cell, elongated and shortened. Just imagine if it is happening within the fluid. That is, okay. Here we have, let's imagine there is the stapes foot plate comes in over here. When it comes in first, there would be some movement of the fluid like this. When that fluid movement is there, the sensory cell which is present here will elongate and shorten. When this happens, the movement of the fluid here will increase and decrease. That is, this energy is taken back and this entire thing is made elongated and shortened, so that these vibrations over here will increase and decrease. This is very similar to a child. For example, when a child is doing a swing, in a swing, once you push the child and leave the child can continue to swing. How does the child do it? By elongating the leg and bending back the leg. Why does that happen? The energy, that is kinetic energy, when the swing is moving, the child can take some of the energy back, give it back to the swing and continue that motion. So exactly same thing happens over here also. So the stapes which moves like this will create the initial disturbance at the cochlea, but that disturbance is taken back by the sensory cells of the cochlea by elongation and shortening and fed back to the same portion, so that the same portion will increase and decrease the vibrations. So this positive feedback makes ear very sensitive. One, it makes you hear very soft sound. Other, it makes you differentiate to very closely spaced sound, that is in terms of frequency. Third, because now this is happening, some fluid will go and hit the stapes back, that will go and hit the all ossicles back, and that will hit the tympanic membrane, and we can measure the sound that is produced by this inner ear over here by keeping a miniature microphone, which is the photoacoustic emissions. Okay. So now all this happens in this portion of the ear. So how does the sound gets converted into the electrical energy? So in the ear, in the cochlea, there are different sensory cells, there are different fluids. Each fluid has different ionic compensation. So depending on this ionic compensation, there could be a positive potential inside the cochlea, or in some portions there is a negative potential. So this portion of the cochlea is called endocochlear potential, where there is a high concentration of potassium ions, because of which there is a positive potential, but the sensory cells have a very negative potential. The resting potentials of the cells are negative. So whenever there is a movement of the sensory cells, the ions which are over here, they will enter inside. Okay, when they enter inside, they make the cells more positive. So when the cells becomes positive, two things happen. This will break and the ions will enter. Cells will enter and it will become positive. Two things happen. In some cells, it will become elongated and shortened, as I said. Okay, when it becomes elongated and shortened, the vibrations will increase. Once the vibration reaches sufficient amplitude, in other type of the cell, that positive ions will start generating the action potential, and that will go on to the brain. So all of these things will happen together. There is a set of cells called outer head cells. In these, they will not generate action potential. When the positive ions enter inside, they will change their shape as shortened and elongated, shortened and elongated. So this increases the overall motion of the cochlea like this. When that energy is sufficient, it will go and hit this portion of the other sensorism, which is called inner head cell. So that will activate the action potential, and that action potential that will activate the auditory nerve, and then the action potential, and the person will start hearing the sound. Now, in this portion, the person doesn't hear the sound. This portion, person hears the sound. But this portion is important to make the soft sound to loud, or to get it to the level where the person can hear. So this mechanism is called cochlear amplifier. Majority, 90% of the people with hearing impairment, whether it is an age-related or whether it is congenital, they have a problem in this portion of the cochlea. That is, the outer hair cells are either dead or they are not functioning because of so many reasons. So because of that, they are unable to hear the soft sound. Only when you increase your loudness, they are able to hear. But the problem with that is, if you increase the loudness, they can hear. But if you increase the loudness further, it will cause pain because they have other portion as normal. So their dynamic range, that is minimum sound that they can detect to the maximum sound that they can tolerate, would be very minimal. So the hearing aids have to work to increase this dynamic range. So compression is one of the techniques I think the next talkers will do, with which the hearing aids are trying to replace this outer hair cells. So as I said, because of these things, amplification happens, frequency tuning happens, compression happens, and also generates the otoacoustic emission. This is just like a byproduct. We don't need this for hearing, but if the person hearing, then this happens. This is like the noise of the transformer. We don't need noise for the transformer to work. We don't need noise, but if the noise is coming, we know that the transformer is working. All of that will get converted into the neural action potential via the synapse or the junction between the sensory cells of the cochlea and the auditory nerve. So sensory cells of the cochlea will have something called neurotransmitters. We won't go to the details of this. In the ear, the type of the neurotransmitter is called glutamate, like you may have heard dopamine. All these are the different neurotransmitters. So in the ear, the neurotransmitter is glutamate. So that gets released, and each of that will start releasing the action potential, and we will start hearing the sound. So once it comes from the ear, it goes into the auditory nerve to different portions along the brainstem and the brain, and finally reaches the cortex, that is the brain. The portion of the cortex that is responsible for hearing is called temporal cortex, which is present just behind this portion of the brain. So the different nuclei that are present are in the back of the head over here. So these are all in the brainstem. So any hit from the back of the head can damage the hearing, because most of this portion is present at the back of the head. Then finally it reaches the cortex, and in the temporal cortex, all of these things will happen. That is spectrotemporal analysis. This is getting the information and dividing them into the spectrum and the time, and seeing at what frequencies, what amplitude, and what are the informations are present. Then we map into a phonological network, that is to making what those frequency and amplitude corresponds to what sounds. For example, when I say per or when I say per, there is a specific frequency and amplitude that corresponds to per, that corresponds to per. That happens. Then basically meaning extraction of the meaning will happen in these areas, lexical interface and in the combinatorial network. The same information is also used for the production. If I have to say per or per, the same information what I hear and present in the brain is converted back into the motor neuron. So if you don't hear or if you are not hearing, it is difficult to produce the sound. Even in people who have learned speech, that is the late onset hearing, if it is not treated for a long time, you may have seen they started speaking loud or they start developing some kind of an articulation issues because they don't hear what they are speaking. So both for speaking and hearing, the same set of information in the cortical regions are used. You have any questions?
Sounds of same thing, close frequencies how will I get differentiate?
If the two sounds of same frequencies are given to the ear, can be differentiated. I mean, we can differentiate. How much we can differentiate? I showed you on the graph. So, for example, here, this is 1 kilohertz. I can differentiate 1 kilohertz from about 980 or 990 hertz. But if it is within that, then I will perceive it as a same one. So that depends on the frequency. For example, at 1000 hertz, you can differentiate up to 4 hertz. 1004 and 996 will sound two different things. Whereas if it is 1002 and 1000, it will sound like the same sound to you. Was that your question?
The pitch value is also different. Pitch value also different. Frequency is same and the pitch value is different.
Pitch is the frequency is what we physically measure. You can have an oscillometer and measure frequency. Pitch is what we perceive, high or low. So psychological perception of frequency is pitch. There is nothing called pitch, we cannot measure it. Pitch is the subjective perception. What humans perceive is the pitch. When we change frequency physically, perception of pitch changes. Like loudness is the psychological perception of intensity. Intensity you can measure with a sub-level meter or a decibel meter. But loudness is what you perceive. When you change intensity, perception of loudness changes.
Is that hairs are growing?
Which layer?
Hairs.
Hair cells, no. There are research going on hair cell regeneration, but once it is damaged, at least for now, like there are stem cell therapies people are trying, but as of now, it is not growable. So that's why we say, once any damage happens to the ear, it is irreversible. Most obvious damage which is avoidable is noise-induced damage. That is, all those hair cells I showed, they are very sensitive to the loud levels of noise. So if you are exposed to the loud noise for a prolonged duration, those hair cells will die. And once they are dead, it is permanent. And ear doesn't differentiate whether the noise is a traffic noise or a factory noise, or you are hearing music through your earphones. All of that can equally damage the hair cells, and once they are damaged, in fact, the early damages are not even perceptible because early damages happens only in the very high frequency and it is not necessary for understanding speech. So we still continue to understand, and if we still continue to use those systems, then they will affect the regions of the cochlea which are responsible for speech. And once it's affected, it is forever. So because that's the reason why age or a noise, all of these things cannot be medically treated. They have to be fitted with a hearing aids only.
Thank you, sir. You are marvelous in explaining the very marvel of pneumonia. I have a basic question that how hearing loss takes place, why it occurs, and how it can be avoided.
I think you have one complete talk on hearing loss. Hearing loss happens because of so many reasons. Like congenital, which one are you saying? Like there are hearing loss, congenital, that is the baby who is born will have a hearing loss. Then you acquire hearing loss during the life. One example is noise-induced hearing loss because you get exposed to the lot. There are certain drugs, like for example, amoxicillin is a very dangerous drug. If you take it in more quantity, that can cause hearing loss. Like all the drugs that are in the mycin category, kanamycin, gentamicin, all of these drugs can cause hearing loss. So many cancers, anti-cancerous drugs can cause hearing loss. Age is a natural cause for the hearing loss. In babies, mostly the hearing loss is because of certain genetic conditions. There are certain proteins which are responsible for generation of those sensory cells. Like gonadotropin is a particular protein that is responsible for generation of those sensory cells. If that protein is not generated in the babies, the hearing loss will be there. There is one complete FDP on causes of hearing loss.
What is the age of those cases?
What is the
Age. So it's from birth to after how many ages it is going to reduce its energy to listening power?
It's not immediate. Like see, by about 40 years, the hair cells will start dying. So if this is the cochlea, every part of this cochlea has got hair cells. So by about 40 years, this portion of cochlea which is in this portion, the hair cells will start dying in this portion. We can hear from 20 to 20,000 hertz. This portion corresponds to 20,000 hertz. This portion corresponds to 20 hertz. Okay? We don't hear 20,000 in everyday life at all. What we hear when for speaking or all our noises are somewhere between 500 to 5,000 hertz. So that is somewhere between this region to this region of the cochlea. So any damage that is happening here is not perceptible. You won't come to know unless you are a musician or you frequently listen to the music. Only music goes into the very high frequencies. The speech or the everyday thing doesn't go to those high frequencies. So by 40 years, degeneration starts. By about 75 years, almost 75% of the population will have hearing loss. Then the hearing loss goes on progress. Each portion has, like there are total about 12,000 hair cells, 12,000 sensory cells distributed in this whole region. So all of them will not die at a time. Gradually starts with the high frequency, moves towards the low frequency.
Usage of the earphones can reduce it.
There are so much of research. We only have done. The thing is, shouldn't listen to the loud, putting it to the 60% of the volume control. And listening to 4 to 5 hours a day has no effect. In fact, there are other research also showing that if you listen to music, there are benefits of listening to the music. But at a moderate level. If you listen to the loud volumes, definitely it will happen.
Either anyway, left and right will have a different hearing capability.
Left and right doesn't have the same hearing capacity. Anybody I test, they have a slightly different hearing capacity in right and left. Some people right is better, some people left is better. There is no uniform which is better, which is not so better. There is no, but both are well within the normal limits, but there will be slight differences between the right and left. So that is why some people prefer to use on the right, phone use on the right side. Some people prefer to use on the left side. There is a slight difference, but both will be within normal. And there are some disorders which can cause hearing loss only on the one side. For example, mumps. It will cause hearing loss only on the side where mumps is a growth here. I don't know whether it's reduced now, but earlier days it used to be. So it will cause hearing loss only on the side where it is growing.
Hello.
Tips means? So ear has two functions. One is well known, which is hearing. The other portion of the ear this portion of the ear is called vestibular system. So this has a fluid, and this nerves of this are connected to the eyes and to the trunk. So now when I am moving like this, the fluid has an inertia. So when I am moving like this, the fluid will not move at a same speed as the head is moving. So because of that, the cells within this, if the fluid is not moving, cell is moving, the cells will get wet. Now that is connected to the eye, so that whenever I am moving like this, my eye will also move exactly towards the same side. My trunk will also move towards the same side. If this doesn't happen, I move like this, my eyes are like this, I am not seeing here. So when I am not seeing here, my balance would be lost and fall down. Now I am able to see there and keep the balance because eyes are moving along with the head. And if this fluid starts moving automatically by its own, then your eyes will start moving like this automatically. So when that happens, you will feel that everything is rotating. When your eyes is moving, you are feeling that I am moving from here to here. You without moving, if my eyes just move like this, then I feel that this whole thing is rotating. So that is called giddiness or confusion.
Since we are using other devices, which produce
There's a lot of research is done on electromagnetic waves and hearing. Nothing is proven. It's, whether it affects or most of the research has shown that it doesn't affect hearing.
sometimes we get
This kind of anecdotal, like people telling, patients telling, that exists, but systematic research many people have done, but there is no effect on hearing as such.
regeneration of the research is genetic. Some people may have hearing loss and early 40 years.
Regeneration. No, it is.
Genetic.
Some may get at 40 itself, some may get even at 88, nothing may happen. It is just like your eyes. Some people have a good eyesight even in the older age, some people don't. That is because of this. That is called positional vertigo. Again, because you are not moving, you moved first, you got up. After that, the movement should have stopped. But those fluids will continue to move, so your eyes will continue to move. So you feel that whole thing is
infants hear the sound which is happening outside.
hearing. The ear is completely developed by about 5 months of pregnancy. When the mother is 5 months after conception, the infant's hearing apparatus is totally developed and can start hearing from 5 months onwards. So even when the infant is in the womb of the mother, infant can hear everything. But the only thing is it will not be able to hear clearly because the infant is in the mother's stomach in the amniotic fluid. So the sound has to go to the stomach and into the fluid and then into the ears of the infant. By then there would be so much of distortion and reduction of the sound. As soon as it comes out, it can hear as well as you and me. It will in fact hear better. But from the day it's born, regeneration starts.
How to improve the
How the
capability?
hearing capability? Means it can't be improved. It is like a predetermined level. You can make certain things not deteriorate.
More than what he is supposed to be improve. Any exercise like that? What are the precautions?
There is no precautions. Like only thing is you can avoid loud noises. There are some research which has shown that listening to mindful, moderate music will prevent the degeneration to certain extent. And like any other system, the balanced diet, good vitamins and balanced diet will help. That is called tinnitus. Again, I said now these hair cells are functioning in this particular manner and we are hearing the sound. If some damage happens to this, the brain will not hear any sound. So in order to, the brain has never experienced that kind of a silence before. So in order to compensate, the brain will start working more. So one of the theories whenever there is a hearing loss, because brain is doing an overcompensation, you will start to hear the sound even when it is not there. That is the ringing sound. It usually happens in the regions where these hair cells are lost. So brain will try to compensate for the reduced input from those regions, and it will start overworking. So you will start to hear the sound in these regions where it is not there. So because of some this kind of a disorder, it happens. It is a symptom of an auditory disorder. Most 90% of the hearing loss people will have that tinnitus. Some normal hearing people also can have some tinnitus or that ringing sound. If some, there is a very mild damage to these structures.
Firstly, I would like to thank Dr. Ajith Kumar for an excellent and enlightening talk on anatomy of ear, hearing aid affects cochlear physiology. Overall session was very clear and it was informative. Now I request Dr. Chandrasekhar M. Patil, Professor and Head, Department of ACE